In this lesson, we will create our first application. In this section, we will create a new project and VI. Now, I'm going to show you how to create a new project and a new VI. To create a new project, go to the Projects tab, and then click Blank Project. I'm going to name my project Simple VI, and click Create. So first I'm going to save my project by clicking Save Project. And I'm going to save this on my desktop and call it Simple VI. So it'll create a Simple VI folder here as well as a .lv project file. So now I'm going to click Save. And just to show you that, if I go to my folder and I go to my desktop, I see that my Simple VI folder has been created. And here we've got our .lv project file as well. Now let's create a new VI. I can click on Add Item and click VI. And now I have a VI that's been added to my project. Instead of calling it something generic like function, I can rename it here and call it, let's make a straight line equation VI. Okay, so now my name has been changed. And what I can do is I can save that as well. So if I go to Save, I can do Save Straight Line Equation. And now my VI has been saved as well. So if you look at our files, now I have not only a .lv project file, I also have my straight line equation.gvi file. Now let's make the panel. So the panel is the user interface, so this is where we want to put down our controls and our indicators. So to create a straight line equation, which is y equals mx plus b, I'm going to need a numeric control. So here, this is where you find your palettes. So you can see there's the numerics here, there's buttons, there's text. In this case, I need a numeric control, which is right here. So I'm going to select that, place it down, and I can immediately rename it. So let's call this one slope. You can also zoom, so I'm going to go over here and make this a little bit bigger. Let's make it 150% so you can see it better. So now I'm going to place another numeric control down, and I'm going to call this one X. If you already know what control or indicator you're looking for, you can also click on Search here and just type in the name of what you're looking for. So in this case, I'm looking for a numeric control. I can find it right here. I'm going to place this down, and let's call this one Y intercept, otherwise known as B. Now I'm going to select these, and I'm going to just move them up a little bit. And I'm going to put a numeric indicator down, which is my output, and call this one Y. Now let's create the code for our VI by going to the diagram. If I select diagram, this is where my code and logic go. All my controls and indicators now show up as terminals that are in my unplaced items tray. So to place them down, I can just click the Unplaced Items tray, select my slope terminal, place this down. And if you want to select multiple items at once, I can hold the Control key down and select multiple items. And that'll allow me to place them all down in a row. And my Y is going to go on this side. So my equation that I'm trying to do is m times x plus b equals y. So to find our different nodes and functions, we can find them in our palettes here. So just like on the panel, we can go through different palettes here to find our nodes. So in this case, I'm looking for the multiply, which would probably be under the math palette and under numeric. And here we see the multiply node. So I'm going to click it and place it on my diagram. Now I'm going to wire this up by left-clicking, and then I'm going to left-click again to attach it. You can also left-click, and if you want to create bends yourself, you can left-click in multiple places to get a nice bend there. So the next thing I need is Add, and if I know the name of my node, I can go to the Search button, type Add. I found it. I'm going to place that here. Now I'm going to left-click here, left-click here again. And then for B, I'm going to left-click and I can do multiple left clicks to make bends and wire this up. Another useful tip is if you want to clean up this wire, you can right click and select Clean Up Wire. Finally, I'm going to wire the output of the add into my Y. So now let's go to the split view. If you want to look at the panel and the diagram at the same time, I'm going to put in some values here. And now let me run my newly created VI. So that's just a quick example of how to create a new project and a new VI. When you are developing a VI, the position of your mouse cursor on an object determines which tool is active. For example, to operate on a control, like changing a button value, you want to move the mouse cursor near the middle of the control until the mouse cursor looks like this. Then when you click, you will operate on the control. To change text, move your mouse over the text until the cursor looks like this. Now when you click, you can modify the text. To move a control, move your mouse near the border of the control until the cursor looks like this. Then you can click and drag the control to move it. To resize a control, move your mouse over any of the small blue resizing squares. Then you can click and drag to resize the control. Lastly, to wire objects on the diagram, move your mouse near an input or output until the wiring cursor appears, and then click to do the wiring. Now I will show you some wiring tips. If you need to select a wire, you can click the section of wire you need. If you keep clicking the wire, you can select more wire sections connected to it. Click on any empty space to deselect the wire. When developing a VI, sometimes you might end up with broken wires. You can either remove each broken wire by selecting a wire and pressing delete, or you can press Ctrl B to remove all broken wires. If you want to clean up a wire, you can right-click the wire and select Clean Up Wire. If you want to clean up a section of code, you can select the section and click the Clean Up button on the toolbar. If you want LabVIEW to try to clean up the entire diagram, make sure nothing is selected and then click the Clean Up button on the toolbar. Now let's go over some different ways to search for controls and nodes. First, you can browse the palettes for available controls or nodes. Second, you can click on this search button to search for controls or nodes by name. Then you can select an item and place it down. From the search results, you can also click this Show in Palette icon to view the palette that contains that item. This is helpful if you would like to see related items and palettes. Lastly, you can search for a control, node, or term in the global search box up here. This will do a global search, which returns results from the menu and toolbar, Learning tab content, the online manual, palette items, and more. Let's talk about how to make your code more readable, both to yourself and other developers. You can make your code more readable by labeling constants to specify their purpose. For example, I can select this constant, show its label, and modify the label to make the purpose of the constant more clear. You can also label wires by selecting the wire and typing in a wire comment. You can also create comments on the diagram by double-clicking empty space and typing. Use comments to document the logic of your code. Similarly, you can create free floating text on your panel, which you can use to provide information to your user. Lastly, you can save space on the diagram by docking a constant that a developer does not need to see. Do this by right-clicking a constant and selecting Dock to Node. You can hover over a docked constant to see its value. If it is helpful for a constant to always be visible to a developer, do not dock it. You can undock a constant by right-clicking it and selecting Undock from Node. In this section, we will create and configure common data types that you will use in your applications. Use Boolean controls, indicators, and constants to enter and display Boolean or true-false values. To place down a Boolean control or indicator, you can go to this palette. Notice that in the Items tab, you can configure the default value of the control. The default value is what the value of the control will be on the panel each time you open the VI. You can also set the Boolean to either a control or indicator. For this Boolean, I can also modify the text on the button. Lastly, notice the mechanical action setting. This important setting determines how the Boolean control behaves. Let's take a look at the two most common types. First, let's examine the latch when released mechanical action behavior. Latch means if you click the Boolean control, it will change its value, and once LabVIEW reads the value, the Boolean control will reset back to its default value. This LED represents when LabVIEW has read the value of the Boolean control. When released means the Boolean control will only register a click if you click and release your mouse button while your cursor stays on the Boolean control. If you click and hold your mouse button on the control, and then move your cursor off the control and release your mouse button, then the control will not register the click. This is a way for a user to cancel their mouse click, similar to most software applications. When I do this, notice that the LED does not turn on because I am releasing my mouse button when my cursor is off of the control. Latch behavior is common for things like OK buttons and stop buttons. Now, let's examine the switch when released mechanical action behavior. The when released part acts the same as I just described. Switch means that if you click the Boolean control, it will change its value and stay at the changed value. Switch behavior is common for things like a Boolean configuration or toggle setting or power button. Here, we see some common examples of Boolean controls and indicators. You might want your user to be able to specify whether or not to log data to a file, or to choose between serial and GPIB communication, or turn the power off or on, or to be able to click a button. Also, you might want to display Boolean data in an indicator, such as whether a threshold has been exceeded, or whether a digital line is high or low. Here, we see common examples of how you might use a numeric data type. You might want to allow the user to specify how many samples to read from the acquisition hardware. And you might want to display a measurement result. You might need to use a numeric constant, such as a mathematical constant or conversion factor. Your requirements for numeric data will vary depending upon your application. To ensure that your VI functions effectively and efficiently, it is important to select the appropriate format for your numeric data. In LabVIEW, we call those formats representations. LabVIEW represents numeric data as floating point numbers, signed integers, unsigned integers, and complex numbers. Numeric data types differ in two ways: the number of bits they use to store data and the data values they represent. To choose the representation of a numeric control, indicator, or constant, you should click the object, go to the Items tab, and choose the representation that best fits the range and precision requirements of your data. Before we examine each numeric representation, let's look at how LabVIEW stores data. LabVIEW stores data in memory for controls, indicators, wires, and other objects depending on the data type of the object. For each numeric object, LabVIEW allocates an area of memory that is at least 8 bits wide. Depending on the required range and precision of the data object, the area of memory that is allocated can range from 8 bits to 128 bits wide. Certain bits in this memory allocation are defined by LabVIEW to store specific elements that comprise the number, such as the fractional portion of the number and its sign, whether the number is positive or negative. An unsigned integer is any whole number greater than or equal to 0. In LabVIEW, unsigned integers may be 8, 16, 32, or 64 bits wide. The bit width provides for the required range of possible numeric values. Click on each numeric representation to learn more about it. Signed integers are similar to unsigned integers, except that they can be positive or negative. The most significant bit determines the sign of the number. Because of this, the absolute range of a signed integer is half that of its unsigned counterpart, but the total range is just as wide. Fractional numbers are represented by multiple floating point formats. Floating point numbers have a very broad range and degree of precision. Double precision is the default format for numeric objects. For most situations, use double precision floating point numbers. Use single precision floating point numbers when memory savings are important and you will not overflow the range of the numbers. In addition to signed and unsigned integers and floating point numbers, LabVIEW also supports complex numbers. For more information on these formats, refer to the LabVIEW help. It is possible in LabVIEW to wire an object of one numeric representation to an object of another representation. LabVIEW automatically converts from one data format to another. This is called coercion. LabVIEW coerces the data type that does not result in fractional data loss. In this example, when adding a double precision floating point numeric to a signed 32-bit integer, LabVIEW coerces the signed 32-bit integer to a double precision floating point numeric, and then adds the two values together. If both data types are integers, LabVIEW coerces the data type with a lower maximum value to the data type with a higher maximum value. In this example, LabVIEW coerces the signed 16-bit integer to an unsigned 16-bit integer. Because LabVIEW attempts to coerce a negative value to a data type that does not support negative values, the add node generates a value of 65,531 instead of -5. LabVIEW places a coercion dot on the diagram node to alert you that the value passed into the node has been coerced to a different representation. In certain coercions, coercion dots may lead to an increase in memory usage and execution time, and decrease in accuracy. In the case of the previous example, coercion resulted in very inaccurate data that could impact the effectiveness of your application. To eliminate coercion dots, match the output data type of the control or constant to the data type of the receiving terminal. Sometimes, though, it's simply not possible to select matching representations for objects and terminals. In those cases, the best solution is to use numeric conversion nodes. When converting representations, be careful to convert in a way that does not cause you to lose data. Here, we see some examples of using the string data type. You can use a string control to allow the user to input their username. You can use a string indicator to display a status string to the user. You can also use string constants on the diagram. To place down a string control or indicator, you can go to this palette. The Items tab shows your configuration options. If you enable the Show Escape Sequences setting, your string control will display spaces as /s, new lines as /n, and tabs as /t. You can also change the font of your text. Set scroll bar settings. Set the default value. Choose your enter key behavior. Choose if you want all text to be selected when a user clicks the string control. And change to control or indicator. On the panel, an enum appears as a predefined list of items, and the user can select one item. On the diagram, the enum represents the selected item as an integer. In this example, scope would be represented as a 0 on the diagram, and DMM would be 1, and fgen would be 2. Using an enum is useful if you would like to limit the user to only predefined items to choose from. To place down an enum controller indicator, you can go to this palette. Go to the Items tab to define your enum items. Notice that the scope item corresponds to a value of 0, DMM to 1, and fgen to 2. Notice that on the diagram, the enum terminal is blue, which indicates that it outputs an integer value. You can choose a visual style for a control or indicator by going to the Items tab. Here, you can choose both a style and a color. To give multiple controls and indicators a consistent look, select them all and give them all the same visual style. In this section, we will learn how to build a VI that acquires, analyzes, and visualizes data from an NI DAC device. Get started with acquiring data from an NI DAC device in a VI. First, create a measurement panel task. Then, use the measurement panel task in your VI. Starting from a new project, I will create an analog input measurement panel task. Now, I'll configure it to acquire temperature data from a thermocouple. Now, I will create a VI where I will access this measurement panel task and acquire data. On the diagram, I will begin by placing down a DAC MX start, and I can right-click the task input and create a constant, and set that constant to the thermocouple task that I just created. The DAC MX start starts the acquisition. Then, I will place down a DAC MX read, and I will set the data format to a single floating point value, and select single channel, and select single sample. Then, I will create an indicator to show the single sample of acquired data. Next, I will place down a DAC MX clear, which will safely clear the task and release any resources. Lastly, I will connect the task wires so each node is operating on the same thermocouple task. Now I will run the VI and acquire data from hardware. This is an example of a VI that acquires, analyzes, and visualizes data. This section of code acquires data. This VI acquires a temperature from a thermocouple measurement panel task. This section of code analyzes the acquired data. In this example, the analysis code checks if the acquired temperature exceeds a maximum threshold and selects a corresponding string. This section visualizes data by displaying relevant data on indicators on the panel. Now I will show you how to create a DAC MX Bi using a measurement panel task that acquires multiple hardware time samples from a single channel. Notice that this project already contains an analog input measurement panel task. The Task tab defines the sample rate. Here we see the sample rate is 2,560 Hz, which means this task is acquiring at a rate of 2,560 samples per second. Now let's take a look at the VI code. We already have a DAC MX start with an AI voltage task constant. Next, I will place down a DAC MX read, and I will set the data format to floating point, and select single channel, and select multiple samples. I can see these same configuration settings in the Item tab. Next, I will right-click the number of samples input and create a control, and then I will create an indicator to show the multiple samples of acquired data. Lastly, I will place down a DAC MX clear and connect the task wires so each node is operating on the same analog input task. Now I will run the VI and acquire multiple samples of data from hardware, which acquired the samples at a rate of 2,560 Hz. You will learn how to create and use array and waveform data types in a later lesson. When acquiring data from an NI DAC device, you can take the measurement panel task approach or the full DAC MX API approach. The full DAC MX API approach replaces the measurement panel task with DAC MX nodes. The measurement panel task approach is intended to help you get started. To help simplify your initial ease of use, the channel, timing, and triggering settings are all contained in the measurement panel task. The disadvantage of this approach is that you must keep track of a separate measurement panel task file, and in order for you to modify a channel, timing, or a triggering setting, you must make that change in the measurement panel task. You cannot make those changes directly from your VI with this approach. On the other hand, if you use the full DAC MX API approach, you use DAC MX nodes on the diagram to configure channel, timing, and triggering settings. Therefore, you no longer need a separate measurement panel task, and you can programmatically configure settings in your VI. In this example, the user can configure settings such as the channel, measurement range, sample rate, and number of samples to read, all from controls on the VI panel. As you get more comfortable programming in LabVIEW and need more flexibility, using the full DAC MX API will be the recommended approach. The full DAC MX API programming flow starts with creating your DAC MX task, configuring the task, then starting the task, reading or writing data, and finally clearing the task. To create the task, use the DAC MX create channel node. To configure the task, you can use the DAC MX timing node to set the sample rate, and use the DAC MX triggering node to set up a trigger, and use the DAC MX properties node to configure additional and advanced settings. The start, read write, and clear nodes work the same as the measurement panel approach. Here is an example of a VI that uses the measurement panel task approach. Notice that this VI is tied to the My Analog Input Voltage measurement panel task file. I can change the number of samples in this VI, but if I want to change the channel, sample rate, or other settings, I need to go to the measurement panel task to make those changes. In contrast, here is an example of a VI that uses the full DAC MX API approach. All the DAC MX configuration settings are accessible in the VI. Notice that I can change the channel and sample rate within the VI, and there is no need for a separate measurement panel task. In this section, we will learn how to build a VI that acquires, analyzes, and visualizes data from a non-NI instrument. The typical instrument driver API programming flow is to initialize the instrument, then configure the instrument, then initiate or start the instrument, then read or write instrument data, and finally close the instrument. Some instrument drivers require you to initiate the instrument, and others do not. When acquiring data from an instrument, you should start from an existing instrument driver example VI, because the example VIs are intended to show you the recommended way of programming that instrument. This particular instrument driver example initializes the instrument, configures the instrument settings, reads a single point from the instrument, closes the instrument, and checks for errors. After starting from an instrument driver example VI, you can then add your own analyze code and visualize code. You've completed this module. Here is a summary of what you've learned.